right, welcome everyone. And we're both happy to be here to talk to you about optimizing Java workloads for containers. You may have heard that Java doesn't run very well in small containers. It uses too much memory and too many resources. Or you may have heard that native images are really the only way that you can get fast startup for your Java applications. In this talk, we're going to tell you a lot about the technology investments that my colleague and I have been making in Java virtual machine technologies to improve the state of Java startup performance and how well Java runs workloads in containers and in the cloud. And we're going to be telling you about this in the context of IBM Semeru Runtimes, which is a JDK from IBM, and that's our icon on the right-hand side there. Next slide, please. So just to briefly introduce who we are, my name's Mark Stoodley. I'm a senior technical staff member at IBM and the chief architect for IBM Java. I'm also a project lead for a couple of open source projects, Eclipse OpenJ9 and Eclipse OMR. And I've basically been a developer working on just-in-time compilers and JVMs, building, testing, servicing, and leading the teams that do those things for the last 20 years. Vijay, I'll let you introduce yourself.
Hello, everyone. I'm Sundaresan. I'm a senior technical staff member at IBM Toronto, and I'm the WebSphere and Java performance architect. And like Mark, I've been writing compilers and JVMs for close to 20 years, and I work on the OpenJ9 and OMR projects as well.
Great. Thanks, Vijay. And next slide. So we work for IBM. IBM has lawyers. They like us to put slides up like this at the beginning of our talks. Next slide. So basically just all the legalese. So yeah, let's go to the outline. So just to give you a brief outline of what we're going to be talking about today, I'll start off with just kind of a refresher about what IBM Semeru Runtimes is, kind of place it in the industry and let you understand what it is and how we build it and what it's for. We're going to spend some time going through Semeru and the various technology investments that we've made in the JVM and in our runtime for running Java workloads in containers and in the cloud. We're going to tie some of that together at the end with a bit of a summary of kind of what the guiding principles are that we use in Semeru for performance and specifically for cloud performance. Because it's a way of, I think, explaining why our perspective on Java performance in clouds and in containers is different than what some of the other teams out there are portraying. And in particular, I'm going to contrast it with the native image approach to Java performance for cloud native Java. Finally, we'll tell you how to get Semeru runtimes and just do a brief wrap up of the points that we've made in the talk. So next slide, please. So the first point is that IBM Semeru Runtimes is, in one way, it's just like all the other Java distributions that are out there that all of the other vendors have. It starts with OpenJDK. It uses the OpenJDK source code and class libraries in order to ensure a consistent Java platform behavior for applications that are running on the platform. And IBM is obviously the one over on the right-hand side there that I've circled in red. And we have two editions. I'll talk more about that in detail in future slides. Next slide, please. So I said that we're kind of just like all the other vendors, but in a way, we're very different than all of the other vendors as well. There are only one JDK vendor that uses the Eclipse OpenJ9 JVM in its JDK, and that's our Semeru Runtimes. And it really provides some very special performance characteristics that are really well suited for running Java workloads in the cloud. And this is what this talk is all about, to explain that to you and how we got there. Next slide. So OpenJ9, if you're not familiar with it, is an open source Java virtual machine that has been tuned and configured differently, in particular to emphasize performance characteristics that are useful for running Java in containers and in the cloud. So I've just highlighted in red the website there if you want to learn more about Eclipse OpenJ9. We're not going to focus too much on it in the talk, but that's where you can go to find more information about what OpenJ9 is, how it works, to get some performance data that backs up some of the claims that we're going to make in this talk, etc. Next slide, please. This slide basically shows very quickly how we build IBM Semeru Runtimes. So it is an open source JDK. All of the components that we use to build Semeru Runtimes are open source. So the open source OpenJ9 is taken directly from upstream and put into the Semeru Runtimes. We have an open source fork of friendly fork of OpenJDK, which contains a few modifications that are needed to build it with OpenJ9, and then we use that to build Semeru Runtimes. We take the release ops and all of the scripting and build scripts and all of the test Aquavit scripts from the Adoptium, the Eclipse Adoptium project, and we use those to build IBM Semeru Runtimes. So we're leveraging a lot of community efforts here that are oriented towards building a solid Java distribution. And then we put out IBM Semeru Runtimes at no cost. We make it available at no cost for everyone to use. We make it available in 2 editions. One is in what we call the open edition. That one comes with the standard GPL v2 plus class path extension license that virtually all the Java distributions have. And we have not run the Java certification tests on the open edition. Then we also have a certified edition, which we release under an IBM license. And this one, we have run the Java certification tests. So the basic differences there are which license it has and whether or not the certification tests have been run against the code. Otherwise, they're 100% functionally equivalent. Next slide, please. So this is kind of our banner slide. I'm not going to go through this in great detail, but I did want to emphasize a couple of points. So the Eclipse OpenJ9 Java virtual machine has basically been the foundation of IBM's Java-based software for almost 2 decades now. It's a very strong investment in Java virtual machine technology that we've been doing for our platforms and for our software and for our services. And if you know IBM, that's basically Fortune 500. So you know that this thing's been put through its paces and it runs a lot of workload. In fact, it's very likely that a part of your paycheck, when you get your paycheck every 2 weeks, a part of that, making that happen probably runs a little bit on the OpenJ9 JVM in some way, shape, or form. It's no cost. As I said, it's very stable, secure, high performance, cloud optimized, available on a wide variety of platforms, and ready for development and production use. The name I wanted to just point out is taken from Mount Semeru, the tallest mountain on the island of Java in Indonesia. So I like to say it's the part of Java that's in the clouds, and in homage to it being well optimized for Java in the cloud. And then the right-hand side there kind of points at some of the performance figures, which we're going to go into some more detail on the technology and the capabilities here, rather than focusing on these numbers. But much smaller footprint, much faster startup, faster time to ramp up in very constrained environments, etc., are the reasons why we call OpenJ9 an optimized for cloud runtime. Next slide, please. All right, so let's sort of start circling over to the cloud and try to understand why is the cloud anything different for Java? Like, why does Java have to do anything different for the cloud or for containers? Next slide. The reality is that the characteristics of the cloud, the way people use it and what people expect from it, have really need to be factored into the performance perspective you have when you're designing a JVM to run Java workloads. So the first thing, as everyone already knows, right? Cloud is compute on demand, right? You get a bill for the resources that you use. It's front and center. And so, the more resources that you use, the higher your bill is going to be. It's plain and simple. Many people are migrating to the cloud trying to lower their capital costs and operational costs. So having that bill right in front of your face telling you how much you're using really brings an increased focus on trying to reduce resource usage in order to save money. This has always been true to an extent, but the cloud computing model just kind of puts it front and center in everybody's front view. If you tie this together with some of the architectural trends that we've seen in the last few years, people aren't designing huge monolithic Java applications anymore. They're decoupling all of the effort in their application instances and building microservices that can be developed independently and can be very easily worked on and tested independently. And that means that instead of one big JVM where you have the opportunity to amortize some of the overheads that Java is famous for in terms of extra CPU usage and extra memory usage, you have a lot of little instances, and those little instances are more difficult to amortize. In all of those, each individual instances, it can be more difficult to amortize those overheads, and that can put additional pressure on how much resources you're using to run a particular workload in the cloud. Now you can couple that. Another factor that's happening here is that when you have all these microservices, people are scaling up and down the number of instances of a particular service to accommodate how much load is present, right? Again, in this quest to reduce resources, you don't want to have lots of of instances sitting there idle, not doing anything, but you're paying money for the resources that they're allocated to. And so you see more frequent deployments, right? You see, and that brings an increased focus on the startup time for instances, because instances are being created on the fly more regularly. As your load ramps up, you create more instances, you have to start up more instances. And so that startup time that Java is famous for is something that's happening much more regularly now in the cloud. And I'm going to summarize startup as kind of time that you're paying for resources, but you're not making money. So again, it's a very important thing to focus on, because it goes to that bottom line, the amount that you're paying for your workloads. Now, because it's Java, the kicker here is, because it's Java, you don't really control the actual resources that are being used to run your application, right? I mean, you can put limits on it, you can kind of draw a box around it, but in terms of how much resource is actually being used by the Java virtual machine, it's managing the resources on your behalf, all of the physical resources. And so if you really want to have an efficient system here, you have to rely on the JVM to properly optimize the use of resources for you. And it needs to do that while accounting for a number of different performance metrics. Next slide, please. Now, this slide lists a number of performance metrics, some of which may matter to you and some of which may not. The point is that the collective set of people who run Java workloads on JVMs, a bunch of people will care about each one of these metrics, and they'll care about them to varying degrees. Now, when we're, as JVM designers, looking at how we're going to augment and enhance the Java virtual machine, all of the design alternatives that we have, everything is trade-offs in engineering. So, all of the various options are going to have, different impacts on these metrics, and we have to choose what are the best designs in order to achieve the goals that people have for these metrics. Different users are going to have different goals, and if you took that to the extreme, that could drive very different design decisions here. And there's no single right answer, because what you want is what you want, what I want is what I want. And just because we want different things doesn't mean either one of those is wrong. It just means that we have different needs for the JVM. Now, we have a wide variety of use cases in containers, and we can't be too specialized in this. But if you look at the set of requirements that people have when they're running Java in containers, they might differ somewhat from the requirements that people would have when running Java in a more kind of bare metal type environment. So these different goals for Java in containers leads JVM developers to balance these performance metrics differently, and that reflects in different design decisions. And that's what this talk is about, is talking about some of the different decisions that we've made as JVM developers in OpenJ9 to enhance or to not enhance various technologies inside the JVM to provide this better cloud optimized experience. Next slide, please. So at this point, I'm gonna hand over to Vijay, and he's gonna take you through a bunch of the work that we've done previously in this space.
Thank you, Mark. So as Mark said, the way we approach Java performance in the cloud is really around looking at it in terms of the customer is paying for everything, all the computing resources that are there. And so the maxim we go by is the one mentioned at the bottom of the slide here. We try to keep each container small, and we try to scale out new container instances quickly. So this overall strategy gets divided up into 4 pillars that are shown on the slide. There's some fairly easy to wrap one's head around type stuff, basic stuff like keep the deployment small. The tricks that one can use there are probably well known to you, to use a JRE instead of a JDK. Use the excellent JLink technology that's there in JDK 11 and newer releases to minimize the dependencies. But then there are also other things that we do in OpenJ9 in the JVM around recognizing resource limits imposed by the environment that are quite different. So for example, table stakes is really to recognize the number of CPUs and memory limits allocated to the container. But we also do other things, like we have different defaults for inside containers, because we can reason about the fact that there's only one significant Java process that's going to run inside the container. So we can allocate a larger proportion of the overall physical memory that we see assigned to the container to that process. And we also have options specifically tailored to run inside containers. So for example, we have an option that allows you to specify MX not as an absolute value, but as a percentage of the overall container memory. OpenJ9 is quite well known for being frugal with memory use. So this is just one of the general JVM characteristics that works well in shared environments using computing resources judiciously. We also have an idle mode where we detect that the application is not using CPU cycles and proactively go and release memory and disclaim some memory to reduce the memory footprint. And there's an option called Xtune Virtualized, which allows you to further skew the balance in favor of CPU and memory reduction. That brings us to startup time, which Mark alluded to as well as being crucial in cloud optimization. And it's frankly the area we've done the most amount of work in the last few years. So we've always had good technology around startup time. We have this shared class cache technology that you can Google and get more information about online. But basically, adapting shared class cache technology to work well in containers, we've done several steps along the way. One, we embed a shared class cache in the Semeru images itself, and we make it easier for applications built on top of that image to build shared class cache layers of their own. To that end, we introduced a multi-layered shared class cache, or we made our shared class cache multi-layered to mirror the container layers that exist. And basically, it allows you to build a shared class cache layer at each container layer if you desire, and they'll be considered as one by the JVM. Another sort of consequence of this is that we need to find a good way to bundle our AOT code, ahead of time compiled code that is part of the shared class cache, into container images and ship them around. It becomes a lot like a static executable at that point, in that we're only taking advantage of the minimum set of architecture features in the AOT code that we produce, a feature that we call portable AOT. So we enable portable AOT code when we're running in containers. So all these features have already delivered. They're all shipped already and are available in OpenJ9 builds for pretty much a year, maybe even more than a year now in all these cases. Next, I wanted to switch tracks and talk about two very recent innovations, but they're at different levels of maturity. So the first innovation I wanted to talk about was Semeru Instanton, which is a project we have been working on over the last 18 months or so. And in a nutshell, it's basically a full process snapshot restore to dramatically accelerate startup. I'll get into this more in the coming slides. And we've been very fortunate that we've had the opportunity to co-design this feature with the Open Liberty project, and having that stakeholder involved in the co-design of this project with us. And you can see probably in the coming slides how that has influenced the design, and really we've thought about several issues because Liberty is using this technology as we have been developing it. The second technology is around Semeru Cloud Compiler. This is a project that we've talked about before in the context of OpenJ9 under the name JIT Server. And this has been around for a few years, except that now we've GA'd the technology at the project. So this is a fully supported feature that we have in the project on our Linux platform. So I'll talk more about that in coming slides as well. So first, Semeru Instanton. So first of all, what is this technology that we're calling Semeru Instanton? The goal for this technology, if you look at the bottom line on this slide, is encapsulated there. We want to achieve instant startup without limiting programming model and capabilities substantially. So what this technology builds on is this Linux CRIU capability to snapshot and restore a process. And this is a well-known capability out there that basically snapshots the process state, including the memory pages that are in use, file handles, network connections, etc., captures the overall state of the process and writes it out into what it calls CRIU snapshot image files. And then you can invoke CRIU to restore from those snapshot image files, and the process comes back to life and continues on from where you left off. So the basic idea is to do certain phases of the startup up until you take the snapshot, and then you ship a snapshot along with your container image, and then bring back the process to life using a CRIU restore command inside the container, and that picks up from where things were left off. So obviously it's faster, much faster, as I'll show soon, because it only executes a subset of the startup work that's needed. And we've done several pieces of work, both in Semeru and in the Liberty application server, to make it easier for you to consume this technology. So the image or the pictures here show how we visualize this. There's a build time and a runtime. Just like there is a native image where you build a native image, here you build your snapshot file. So how that happens is this JVM starts up with your application running on top of it. You reach a particular snapshot point where you want to initiate a snapshot. You can ask the JVM to run certain pre-snapshot methods for you. So prepare yourself for taking a snapshot. The JVM itself is in the driver's seat as far as initiating the snapshot is concerned. So it is the one that produces or calls into CRIU to produce the snapshot, and then it exits after taking that snapshot. Now, as I said, you would bundle the snapshot image in your container, and you can restore from that snapshot image as many times as you want. On the runtime side is where we show this. You restore the Semeru JVM from the snapshot, so the process comes back to life. Then you can run some post-restore hooks to massage the process into the state that you would like. And then the application continues running as though this whole process had not occurred. Now, Mark and I outdid each other in coming up with retro images to represent this. So I apologize for those, but I think Mark won out in that he used the 80s style floppy disk on the right, but you get the basic idea. We take a snapshot and then we restore from it as many times as you want. Now, as I said, this has got to be faster, right? Because you're only executing a subset of the startup. So how can it not be faster? But how much faster? So from this graph on this slide, we show 3 applications running on top of the Liberty application server. There's a simple application on the left called Pinker, which was starting up in 1.5 seconds or so. And with our prototype at Liberty, so there's a Liberty Instanton prototype, which is using the Semeru and OpenJ9 technology underneath. We were able to restore in 128 milliseconds, so over a 10x reduction. We then went over to try a slightly more complex app. This REST CRUD application uses a database, whereas the initial app was very simple, no business logic at all. Here we have a database access, and again, the improvement is over 10x. We went from over 3 seconds to approximately 200 milliseconds. The third app is probably the most interesting of all because it is actually an app called DayTrader 7, which is an EE7 application. So this is not a simple toy benchmark by any means. It's got a lot of business logic in it. And in that case, we were taking almost 5.5 seconds to start up originally. And with the prototype, once again, we're down in that 300 millisecond range or so. So massive improvements, as you can see, an order of magnitude improvements. And so we've been very fortunate that Liberty has been co-designing this feature with us at the Semeru project. And the 2 projects are going hand in hand, and Liberty Instanton is the name that we give the effort to explore the productization of Semeru Instanton at the framework level. So what are the main goals of Liberty Instanton? Usability is one. There's a lot of complexity at the CRIU level, at the JVM level, etc., that really the end user doesn't need to be exposed to. So it's an exercise in hiding all that complexity from the user and ensuring that the framework takes care of everything for you. And then there's the functionality aspect of it. We want to make it possible for an end user to run their applications without changes. So that's an important goal for us rather than only target new applications. Okay, so then I jump into the technology side of things a bit here and talk about how this actually works, because I figured this sort of engineering audience would be interested in that. piece. So the first thing or this slide talks about the different things we've done to make it easy to use. So the first thing is at the Liberty layer, we make Instanton easy to use by just introducing a command line switch to specify the startup phase where you want to take a snapshot. So it's as simple as just saying, I want to start up Liberty, I want to take a checkpoint, and we give you 2 or 3 different options for when you can take the snapshot, and you just pick one of those options. So it's that simple, as I'll show later in the demo as well. Now, which phase you pick to take your snapshot, that affects what your startup time is. If you choose to take your snapshot earlier in the startup process, obviously more work will be done after the restore. But there's also a greater likelihood of a successful restore, I guess, that you won't have done one of the things that might end up defeating CRIU when it's trying to restore the process. We also make it easy to consume by packaging up all the prerequisites into the Liberty container image. So we'll have the right versions of Liberty, which has awareness of this feature, obviously, and Semeru, but also CRIU and the right level of OS support needed to make all this happen. We'll also specify command line options or environment variables to various low-level libraries needed to acquire the relevant privilege level or to just make things work from a snapshot restore. So as an end user, you don't need to worry about this low-level stuff. You can worry about applications written on top of Liberty, basically. We also make it easy for a user to build their container image with a snapshot. So if you go to the Liberty framework page, you can see that there's already instructions that are quite straightforward and natural to help you build an application container image using the base Liberty image. So think of the step to build a snapshot, an image with a snapshot as an extra couple of steps. So you have your application image. What you have to do is start that application and specify the phase at which you want a checkpoint to be taken, and you produce the checkpoint file. You bundle it up and you add another layer with that snapshot file added in to your application container image. So fairly straightforward, just add another layer on top of what you're already doing, essentially. And then the final thing I wanted to talk about to make it easy for the end user, that we have sensible defaults to make the user experience as seamless. So we automatically detect if there is a CRIU snapshot or those snapshot files exist. And if they do, then we'll try to restore from those. If we're unable to restore for some reason, unlikely, but if we're unable to restore for some reason, we will start the JVM, start Liberty in normal JVM mode. So there's no sort of crash and you're unable to recover from it in that sense. My last slide talking about snapshot restore or the technology underlying Instanton. And this is more around what we've done to make it easy for your existing apps to be brought and take advantage of Liberty Instanton, brought to the platform and run successfully on it. So we have the first thing we built is this cooperative hook architecture. So hook is really another word for having like these routines that we run on demand across the Liberty and Semeru. So as an application framework on top of Semeru, Liberty can come along and register hook methods to run at different points of time. And it can specify the order in which different hook methods should run. It can also specify whether it should be run when the JVM is in a single-threaded mode or in a multi-threaded mode. And as part of this work, obviously the framework is very likely running in multi-threaded mode originally, but as part of this work, we've also introduced a single-threaded mode where there's only one thread that's running that's going to go in and take the checkpoint or initiate the checkpoint. So the user has a lot of flexibility around specifying hooks to run and the order and when they'll run, and Liberty already is using this to register several hooks. Now, what are some of these hooks used for? mainly to compensate in differences between the snapshot environment and the restore environment. So if you're running on an older version of an architecture and now you're restoring on a new version of the architecture, that's not so much of a problem. But think of the opposite. If you took the snapshot on a newer version of the architecture and restored on an older one, you don't want to crash because the JIT compiler, for example, produced code that doesn't run successfully on the restore machine or on that CPU. So the way we handle this is we extended that portable AOT code that I alluded to earlier and extended it to portable JIT code. So we generate code basically that only assumes the lowest common denominator and can run on all architectures because JIT code could be included in the snapshot. Similarly, if you had different number of CPUs, different amount of RAM, etc., we handle all those kinds of differences and make it sort of transparent to the end user. Things just work on the restore side, and then we pick up the right number of CPUs and the RAM on the restore side. Environment variables is a big one. This is where working with a real world framework like Liberty really benefited us in that you need to have ways of specifying configuration parameters at deployment time, right? If you're using a framework, you may need to specify some environment variables that are unique to the deployment environment that you're in. So we allow you to do this. Liberty has code that scrapes up new values of environment variables at restore time and conveys that to the JVM, which then updates its view on what the environment variable values are. If you were just going with what CRIU does, it's frozen in time. It's basically only able to pick up the environment variables that were there on the checkpoint side. So we had to augment Liberty to scrape up newer environment variables on the restore side and make those available to the JVM. Now, security is obviously a concern in this as well. If you're shipping checkpoint files in your container images, and we've done some work to create a new bare bones Instanton security provider, which we use before we take the checkpoint or before the checkpoint phase is reached in Liberty. And this is a very minimal security provider, doesn't use any native acceleration under the cover. So it's really easy to clear the state in it before a snapshot is taken. And then we instantiate a full function security provider upon restore. So we consult the security properties file at that point and use it after the restore. And finally, there's a variety of other smaller areas that I won't get into in detail that we also have compensations for already. Things like you don't want the same random number seed to be used in n different containers that are restored from the same image. So we compensate for it, and on the restore side, basically, we do the necessary adjustments so that the different container images restored from the same CRIU image still use different random seeds. We adjust for time. We don't want the potentially large amount of time that elapses between taking a snapshot and doing a restore to necessarily have detrimental effects when you restore. For example, we don't want timers to go off all of a sudden because a day has passed between the time you took the snapshot and did the restore. So we compensate for those sorts of things, both in the JCL, through changes in the JCL that are included in the Semeru JDK, but also in the JVM. Okay, so at that point, I will stop sharing this presentation and switch over to the demo. So I have here a Liberty install. So what I'm going to be showing is really the Liberty Instanton at work, and it's using Semeru Instanton under the covers. So I have a Liberty install already. I'm in the Liberty installation directory. And the first thing I'm going to do is actually to start up Liberty, which you do by specifying this bin server command, followed by run. So run basically says, please start up the server. And I'm going to do it with -- clean on the command line. So basically, this will clean out any pre-existing state from prior starts that I may have done before it starts it up this time. So you can see that it started up fairly quickly, 3.5 seconds or so in this case. So I will shut down that server next. I'll start up the server again, but this time without the -- clean. So in this run, we will take advantage of that initial startup, and it starts up a little bit faster, as you can see, around 2.8 seconds in this case. But this is all still running in normal JVM. So I'll stop the server again now and start getting into looking at what checkpoints can bring here. So I'll first of all check that there is no checkpoint image in the directory in the work area of the framework, because I did the -- clean earlier. There's no images, no checkpoint stuff at all at this time. Next, with that clean slate, I will go and issue the command to generate a checkpoint. So you can see how easy it is on the command line, how natural it is. All you had to do was add, instead of saying bin server run, you say bin server checkpoint, and you get to pick one of the three points at which we offer this capability to produce a checkpoint. I've picked the applications phase, which is the latest phase. So I say, please generate a checkpoint, add applications, and that results in this run where you can see that that option was picked up here. The checkpoint completed and the server stops. So it exited the process on its own. So in the checkpoint run, the checkpoint is initiated by the app server. So the -- so the checkpoint option is picked up by the app server. It's passed down through the APIs into the JVM, which then initiates the checkpoint on its behalf. Okay, so the checkpoint. So we did the checkpoint. Do we have any checkpoint images? And the answer is yes, we do. Now, all these variety of images are what's here are you produced in the image directory in the work area. And because it's produced in the work area here, Liberty is able to automatically detect that these files exist. So let's see what happens when we just issue bin server run now with these checkpoint files in there. You can see that the startup time is super fast in this case. You start up in 0.154 seconds, where earlier we were around that 2.5 second mark. So comfortably over 10x improvement as a result of having the checkpoint. So I'll just go in and do it again and restart again. In this case, it was slightly slower, 0.213 seconds, but still you get the picture. It's an order of magnitude faster than where we started. And the point that I really wanted to emphasize here is this is an actual stakeholders, a real framework out there, and how easy it is to use it. It's not, you don't have to really worry about all those details that I talked about earlier. They're relevant, but only from the perspective of us sharing information as engineers. But as an end user, if you're running applications on top of the framework, it's dead simple. I wanted to make that point. So with that, I'll go back to the presentation and really sort of pick things off from where I left off. Shift to the next slide. So, switching topics now away from Semeru Instanton, because we talked about that a fair bit. What is Semeru Cloud Compiler, which was the second innovation that I was talking about earlier? Semeru Cloud Compiler, also known as JIT Server. So in order to understand what the Semeru Cloud Compiler is, first, maybe good to know or refresh what a JIT compiler is in its own right. So JIT compiler is a component. Sorry.
AJ, sorry to interrupt. Did you want to go back into screen sharing from current slide? Maybe.
Let me check if I can do that.
Second one from the right. Sorry, second one from the left from current slide. Yeah.
Okay. What is JIT Server? For that, you need to understand what a JIT compiler is. JIT compiler is this component within the JVM that compiles bytecodes down to native code and speeds up application throughput as a result. So it's an invaluable part of a JVM. However, it also takes up resources, CPU, and memory. And so the JIT server project or cloud compiler really tries to separate the JIT compiler from the rest of the JVM. So it decouples those two things and introduces more of a client server technique of communicating between the server and the JIT server and the client JVM. The JIT server asks questions to the client JVM about the classes and environment, etc. the server gets those answers back from the client JVMs and sends back generated code or compiled code back to be installed in the JVM's client code cache. So decoupling of the JIT from the JVM actually allows you to scale these two processes independently, like you would scale different services in a microservices application. So think of it as you've made the JVM into a microservices application almost. Okay, so that's what JIT server is, or cloud compiler is. Why would you want to do this? And the slide gets into this. I won't spend too much time on this, but there are two main reasons. One, as you can imagine, by pulling out the JIT compiler from your container, where the rest of the JVM and your application is, we remove the JIT-induced CPU and memory spikes from those containers. So this allows you, the end user, to right-size your containers. You don't have to worry about this phantom component in the container, this JIT compiler component. And instead, you can rely on the resource consumption only driven by the Java application and right-size your containers. This is shown on the figure on the right, where you have all those spikes initially from the JIT compiler, but without those spikes, the application behaves fairly regularly and is much easier to predict, takes lesser amount of memory and more predictable depending on your own application use cases. So there's also another benefit that comes from smaller containers, of course, which is increased container density. You can pack more instances onto hardware and save costs that way. Even with an extra JIT compiler, a JIT server in the mix, it still comes out to be a net positive because there's a temporal aspect to how these clients are requesting compiles. If you put a JIT compiler in JVM container, it's there and it's taking up resources and you have to budget for it all the time. Whereas if the JIT server is separated, even if clients connect to the server at different points in time and request compiles, the JIT server's contribution is actually ends up being lesser than what it would have been if you just put a JIT compiler into every single one of those client containers. So that temporal aspect is very important in getting the increased container density. And the second benefit is, of course, faster time to ramp up to peak throughput. You can allocate more resource to the JIT server, more CPU and memory, which can mean that more compiles can be done in parallel than at the client. We've done several enhancements recently. This is an area of our technology that keeps evolving. And but the feature has GA'd, unlike Instanton, which is still at a fairly early stage. We're 18 months into that project. This one has been in development for at least 3-4 years now. Okay, and I will conclude my section with a look ahead at where we're planning to take these exciting innovations. From a cloud compiler perspective, we're going to try to take advantage of having a server connected to a Java process in other ways. So rather than restricted to just JIT compiled code, maybe we can distribute other artifacts from a server now that we have the base technology. From an Instanton perspective, we want to make these JVMs more configurable and improve the ramp-up time after restore. There's also some really cool things you can do combining these two technologies. So combining Cloud Compiler and Instanton, you can take advantage of the fact that the JVM was restored using Instanton and CRIU snapshots when you are when you're doing cloud compilation. So there's some interesting possibilities there, as well as tooling that could generally help the end user understand their own application better. With that, I will turn it back over to Mark. Over to you, Mark.
All right, thanks, Vijay. So we've got about 5 minutes left, so I'm going to try and scoot through the last few slides fairly quickly and see if we can save a couple of minutes for questions if we have any. So the purpose of this section was really to just kind of talk about how we approach augmenting JVMs for the cloud and trying to bring a performance to Java applications when they're running in containers. And I'm not going to claim that this is an exhaustive list or that it is the complete list, but there's a set of things here that we believe around how we will augment the JVM and how we would get performance. So the first one is, and it's something that we believe quite strongly, is that interoperability and freedom of choice are very important. And this kind of, one way of putting this is that Java specifications are very important, but it's about more than that. It's about making sure that all Java applications are able to take advantage of the things that we're talking about. So get a slide, GJ, I think there's another piece that comes up. Right. So when we're doing work, we're trying as much as possible to adhere to what the Java specifications are. And that means no Java programs are left behind. We're not trying to say there's a class of Java applications that we care about. It also comes down to, trying not to avoid kind of locking people into this implementation. Most of the options that you would use to activate the technologies that we use are things that don't need to be specified on the command line. So that means that if you want to, you can always switch to another JDK implementation, and you won't be locked into ours. You won't get the benefit of the technology activations, but at least you won't have to go and find all the command lines that have the options available, and so on. The second area where we do is CPU and memory should be used as efficiently as possible, basically. And I've provided a list here. There's a bunch of investments that we've made here in having, our object headers have a single word. We're very frugal on our heap growth heuristics. As Vijay talked about, we've found ways to bring our JIT overheads out of the compiler. We have an option called -xtune virtualize that can further use resources even more frugally when you have a very resource constrained container environment, and etc. We believe startup performance is important for elasticity and responsiveness. And we've done a lot of work that Vijay talked about earlier in his section, so I won't go through this again, but just lots of things that we've done here in that space. However, we do believe that dynamic optimization is very important, and we leveraged our aggressive JIT technology here, exploiting the live profile data and all of the improvements that are possible because of it. We don't want to give that up. We think build time is important because developers need to be efficient, and we need to be able to release code efficiently. So we try not to add very expensive steps to the build. And so even our shared cache technology, which has a pre-population step, you do it basically by starting the application, which is no different than running the tests that you have in your CI environment, and should be no more painful than that. Finally, image size is a thing that gets a lot of attention. However, if you're properly applying layers to your shared class cache, it should be only the layers that are changing most frequently. We believe it's the application layers that would be changing most frequently. You don't update the JDK that often. You don't update your framework necessarily all that often, but your application is updating quite a lot. And so it's the size of that layer that matters most. And that's where we try to focus our efforts in making sure that we're not adding substantially to that layer. Now, in contrast, if I have a slide, the next slide, please, Vijay, which essentially puts words into the native image projects line. But I just wanted to provide kind of a compare and contrast here with the native image approach, just to kind of emphasize just how different these two approaches are. So obviously, on the interoperability point, native image basically starts with the premise that there's not going to be any dynamic class loading. So they're taking something away from Java and then optimizing as far as they can, given that reduction in the specification. And we think that's a very fundamental thing, but it's kind of the basic approach that native image has chosen. They do try to use things as efficiently as possible. Everybody tries to use resources as efficiently as possible, but the footprint under load can be less efficient when you're using native images than when you're using the full JVMs, which have access to the full garbage collection technology and all of the other aspects that we've optimized. Native image considers startup performance obviously most important, right? That's one of their big advantages, getting the startup time down into kind of like the tens of milliseconds to low hundreds of milliseconds. But I think, as you've seen with our checkpoint restore and instant on technology, that we're getting down into the same ballpark already. A native image has no dynamic JIT allowed, so it's only image build time optimization. That image build optimization can take minutes to run, and it has to run inside your CI pipelines. And then on top of that, the basic approach is that your application gets compiled together with the JVM. And that does provide a small image, but it means you have to rebuild it every time. And you have to provide that full thing every time when you're downloading an image. So there's some very different approaches here between how we optimize Java using Semeru Runtimes and how native image approaches. And what we're trying to do is basically, not leave any Java applications behind. Let's just go quickly. Yeah. So this is a slide. I don't have much time left, but this is the slide that tells you where you can get Semeru Runtimes. There's a lot of you can get, the downloads are ibm.biz/get-semeru. There are official Docker Hub images. There is the IBM container registry, which has all of our Docker containers available. The Red Hat registry has our containers available. There is if you have a question or you want to talk to the Semeru Runtimes team, you can go to our GitHub repo at IBM Runtimes Semeru-Runtimes, and you can open an issue and talk to us. We have some talks at jconf.dev next week, which are going to talk even more about some of this stuff and talk about some of the how you can get your hands on some of these evaluation technologies, in particular for Instanton. And I'm going to say watch for new blogs next week at blog.openj9.org. And the final slide is just a wrap up, which I think I'm just going to leave up there and won't talk very much to. Semeru Runtimes are runtimes built by IBM. We're trying to make your Java workloads run as well as they can inside containers using the least amount of memory, so they save you deployment costs. We're investing all the time in new technologies to try and make it work even better, including Instanton and the new cloud compiler, which further improves how well Java applications can run inside containers. And we're going to push even further on those technologies and make them even better. And the one point that I want to leave you with is that we don't believe that Java has to be just another language that runs applications in the cloud, right? Lots of different languages can be used to run workloads in the cloud, but Java should really use the cloud to run applications better. And that's what we're trying to do. We're trying to take advantage of the cloud and the deployment opportunities that are in the cloud to make Java better and to make Java workloads run better in the cloud. And with that, I will stop. Thanks everyone for listening.
Thank you.
There is one question in the chat. Can Semeru Runtime be helpful for others, e.g. Tomcat? I think the answer is definitely yes. A lot of the shared class technology and code caching technology that BJ talked about definitely can benefit startup time for an app server like Tomcat or the applications that you run with Tomcat. On top of that, Instanton could be used with it, although we haven't, our investigations have been specifically with using Liberty with Instanton, but there's no reason why that basic Semeru Instanton technology could not also be used with Tomcat.